And it is my pleasure to introduce you the next speaker, Vassili Kolokoltsov, who will tell us on the theory of stochastic quantum master equation, quantum filtering equation for mixed states, and its extensions for interacting particles. So please, Vassili.
Okay, thank you very much for giving me the opportunity to talk here. Very interesting conference, which I'm already taking part in the second time. So the results which I'm going to talk are really very, so to say, fresh. I've just finished writing the preprints and possibly, hopefully, put it on archive in a couple of days. But there are lots of sort of motivations for this work, with which I possibly will start. So these are the paper for, so to say, the motivation. You see, one of the most popular direction in game theory are now the so-called mean field games. So everybody is doing mean field games, and there is also another popular new direction in games, which are quantum games. And it was very natural to try to put these things together, and that's what I have done a couple of years ago. So I developed quantum dynamic games and therefore quantum mean field games. And this development, and well, these are the papers which actually devoted to this theory. And this development led naturally to a new kind of stochastic differential equations. They are similar to the nonlinear stochastic Schrödinger equation, but they are somehow different. And I will try to show you why. They are somehow can be called like infinite dimensional operator valued Makin-Vlasov nonlinear diffusions, something like that. So these equations and their derivation is based on the theory of quantum filtering, which was developed about 40 years ago, essentially by Belavkin, and then in various other versions appeared in the theory. And this is the way to get feedback control for quantum evolutions. So in another way, these are the theory of open quantum system. And this equation can be written in two ways. One is for pure states, which are the vectors in Hilbert space. And another is for
Vassili, I'm sorry to interrupt you, but we still see the the second page with title main sources for the motivation.
Yes, and I am on this page still.
Okay, because you were mentioning some equations. I thought that we should see some.
I will show you equation, yes.
Okay, sorry, I'm sorry.
There are two kinds of equation, one for pure states and another class for mixed states. So pure states are for Hilbert space and mixed states are for density operators. So for pure states, somehow, we are in the theory of stochastic differential equations in Hilbert space. And for this Hilbert space, we have sort of usual eta calculus. But once we are moving to pure states, we find ourselves essentially in the Banach space of trace class operators. And here is somehow the difficulties which has to be overcome, because there are essentially no stochastic calculus for such Banach space. For those who know this story, there are some classes of Banach space like unconditional martingale difference, martingale two type, or so on, and they do not include the spaces like L1, measure spaces, and operator of trace class. So even this statement of these differential equations is sort of non-clear. And at the same time, they do exist, as I said already, for 40 years in physics. And they are stochastic extension of what is also called the Lindblad equation, or basic equation of quantum dynamic semigroup. So how the contribution which I'd like to show is really the theory of this equation, how one can overcome this problem. What I will do here in this my 20 sort of minutes, I will show you these equations, give some comments about them, and will formulate the results. Okay, so this is abstract, which I effectively already told you. So the equation which I'm going to tell can be developed from quantum filtering, but this is very complicated way of doing things, coming from and using the rather complicated quantum stochastic calculus. There are lots of other ways, and some physicists really have written this equation just somehow by physical intuition. And as I said already, the mathematical theory of this equation is a long-standing open problem. I mean, everything is clear for finite dimensions, but once we go to infinite dimensions, there appears this story which I just mentioned to you. So here I mentioned some authors which made important contribution to this story. Yeah, Barchielli, Holeva, Pellegrini, Chebotarev, Fagnola, Quezada, Mora, Rebaleda, and there are some others, so mentioning everybody. So in particular, these people developed the theory of this equation for finite dimensional cases, and also some parts for infinite dimension were mentioned and dealt with by this author. Okay, so now look at this equation. So they are starting from not too complicated one and become complicated. So from the point of view, also I mentioned that from the point of view of stochastic analysis, if we just, forget about the quantum story, so what is somehow the mathematical story here? Mathematical story here that we consider equation with singular coefficient. So this can be considered, this talk can be considered as a contribution to stochastic differential equation with singular coefficients, and we will see why. So let me now introduce you this equation. So the first one is the simplest one. So as I say, quantum filtering can be given for pure states and for mixed states, and even for pure states and mixed states, they have two versions: normalized and non-normalized. So this is the simplest version, which is sometimes called Belavkin quantum filtering equation. So here is the vector, I is the vector in the Hilbert space, H operator Hamiltonian, L operator which gives you coupling with a measurement device. Okay, so also I may comment how one can actually write this equation, how one can guess it. So yes, it can be derived as a very complicated quantum filtering, but in another way, it can be physically look like that. Well, we have Hamiltonian, so this part is just usual Schrödinger. Now we want coupling with observed trajectory. Well, we observe trajectory. This is output diffusion process. So coupling is usually, we take some linear combination of a vector with this output and put some operator. So we add here this L coupling operator. And now where these terms come from? Well, we want to this equation to preserve the expectation squared in expectation square norm should be preserved. So from this assumption, we actually can derive this coefficient. So this is equation for chi, which is not necessarily normalized. It has some other normalization where the chi squared is the density with which this output process y is observed. But if we want to get the equation for normalized state, we have to get chi divided by norm chi. What we see will get much more complicated story. It's very, in fact, difficult to see what it is. Well, here are actually the values. So LS and LA are the symmetric and antisymmetric part of operator L. And here we make some values of this operator L on phi. And here is the same. A little bit complicated story. And this phi is obtained as a ratio chi and chi. And the B is called innovation process, which is linked with this output y in the following way. One can write it a bit simpler if one uses these brackets, which actually denotes the value of operator A on a state phi. Well, still, it's a rather complicated story. Yeah, so this is for pure state. But now if we move to mixed states, then in some sense it becomes simpler, in some sense it becomes more complicated. Yeah, but first of all, I also wanted to mention the result about the opposedness of this thing. It also has quite a long story. So for finite dimensional case, somehow it was sorted quite a long ago, but for infinite dimensional cases, possibly my result in 3 years ago was the first to give this well-posedness for infinite dimensional case. And the main point here is to observe that this thing here is Lipschitz continuous. So once you observe it, which is not quite obvious, but not too complicated, then you can just apply effectively the standard Ito story. And that's the lemma which I formulated, that this mapping from the vector in Hilbert space to itself, and M is the values of operator M. This has bounded derivative, bounded by norm of M, and therefore we have this Lipschitz continuous thing. Now we move to main point, actually. If chi is a vector in Hilbert space, and if we take now chi multiplied by chi hat, then what we get is a density matrix. And you see, for density matrix, equations look a bit even simpler. So this L, this is so-called Lindblad term. So if there would be no this dy, then what we get is very famous Lindblad, Sudarshan, Kazakovsky, Garini equations for dynamic quantum dynamic semigroups. Is effectively the general form of equation which preserve complete positivity. And now if we normalize, if we take the product of normalized vector, then again we get equation which also looks a bit better than for pure states. But as I say, now the problem is how to understand this equation. The very natural, the most natural space here is actually the space of trace class operators, because this is exactly the class on which density matrices or mixed states exist. But as I say already mentioned, it's very difficult to do anything, because in this Banach space, we do not have any Ito stochastic calculus. So idea was to consider this equation not in the space of trace class operator, but in the Hilbert space of Hilbert-Schmidt operators. So yes, we can do it, but the problem here is, and then this part here will be not Lipschitz continuous. So if we somehow move to Rebeta space, Hilbert-Schmidt operator, then we are getting this discontinuous or non-Lipschitz coefficients, so singular coefficients, and we have to deal with this somehow. Okay, so now these theorems about, my theorems are essentially, there are two parts. Theorems about this equation, so how we can build a theory of this story. And then extension of this when we are moving to what is needed for quantum mean field games. When we'll move to quantum mean field games, as I'll show you a couple slides later, there appear here additional interaction term, which makes the story, of course, more complicated. But now with the theory developed, an approach which is developed, we can deal with this, and I will show you the corresponding theory as well. So first, equation 4 is well posed, and you see it is well posed in the HS2 Hilbert-Schmidt operators. What is important here? Well, you see, if you look at this equation, and you see that in the Hilbert-Schmidt, in the class of Hilbert-Schmidt operators, everything here has bounded operators. So well-posedness is obvious. But what we need, it's not just Hilbert-Schmidt. We really need here traces. So we need that the solution preserves the class of trace class operators, which is not obvious. And second, what we need preservation of positivity. So though the general well-posedness is somehow obvious, but positivity and preservation of trace, well, not preservation here, but bounded. Preservation of the boundedness of trace. Here will be preservation of trace. So this part, therefore, preservation of positivity and that the traces remains to be bounded, these are not easy stuff. And in fact, there's quite a lot of discussion, specifically the second part, the preservation of positivity, in all the papers which devoted to this story, and particular authors, which I mentioned at the beginning. They all mentioned, well, this is difficult part in the proof. And there are several approaches which were developed for finite dimensional case. I can mention Barchieli, which uses the link with the pure states, Pellegrini, which use the approximation by Markov chains, and also myself, I use the way of rewriting equation in terms of Stratanovich, and then use the theory of somehow non-stochastic equation. Here I'm suppose developing, I suppose, a bit new still approach, which is close to what is in the book of Barchieli for finite dimensional case, but still a bit better suited to infinite dimensional setting. So there is not obvious thing, and other also not obvious thing with the trace. Yeah. So again, I'm stressing here that once we consider this in the Hilbert space of Hilbert-Schmidt operator, the operator of taking trace is discontinuous. So, well, it's possible to deal with this, but it requires certain work. Now, main theorem, actually, one concerns this equation. Okay, so at least here it is linear, and at least well-posedness in Hilbert-Schmidt operator is already clear. But here we have this trace already. This is non-linear and with trace inside. Yeah? So nevertheless, we can build the solution, and here we use, so that is the theorem that this for this equation 5, this non-linear normalized version of quantum stochastic master equation. Yeah, maybe I repeat, yeah, without this dB term, this guy is quantum master equation. And with this term, which is unraveling, is referred to unraveling in physics, this is the stochastic part. Okay, so we prove the well-posedness when BT is usually a Brownian motion, and preservation of positivity and preservation of trace. And here the main idea, actually, well, there are, and that's also the second important part here is the continuous dependence. If we consider two equations with two here different Hamiltonians, then we have continuous dependence. Expectation of the solution is bounded by some coefficient small in time, and the difference of the norm of H1 and H2. Now the main idea here, well, I mean, there are possibly two main things. First, really to stick to the equation in Hilbert-Schmidt operators, and we'll accept as additional complication the thing that trace is unbounded. And second is really to use the constructive link of equation for mixed states with the equation for pure states. And in fact, if you have initial density matrix, it is positive trace Calas operator, and therefore it can be expressed, by this Gilbert theorem, yeah, that it has pure positive spectrum, so it can be expressed in this way, where EK is some normalized basis in the Hilbert space. And then by linearity, if we want to build the solution with this R0, by linearity, one can build the solution with this initial condition and then extend it and then take the sum. And then the raw solution will come from this solution EKT. Now they are already solutions to pure states. And now one of the main observations again, that we can write this system sort of or equation for each EK as one equation which is exactly the same as pure state Belakhin equation, when we consider new Hilbert space of sequences of vectors in our initial Hilbert space, which I denote L2HPK, meaning that here the norm will be the sum of the squares with this pk coefficients. So here is, as I say, this is possibly the main idea of my approach to the solution, is to see that complicated mixed state equation can be rewritten effectively as pure state in some auxiliary enhanced Hilbert space, and this allows to deal with all kinds of problems like positivity or preservation of trace. Okay, so that's concerning, and you see this actually things which I sort of say done bypassing. I mean, I started when I developed this mean field game story, I started to trying to give a sense to these new nonlinear equations. And then I realized that already even before the interaction, so to say, this theory doesn't exist. But these are now the equations which arise in quantum mean field games. So this is the same as previously, but additionally we have here this interaction term. Yeah, so if you know, say, the nonlinear stochastic equation, forget about everything which comes after this. Then you'll see here standard nonlinear stochastic Schrödinger equation. Now, addition of this additional story, this puts everything from, this moves you from the closed quantum system to open quantum system, or they can be looked also as continuously observed quantum system. And in the simplest way, this A is bounded. Yeah? And of course, this appears if you take, say, bounded potential of interaction. Of course, it does not work when you have some Coulomb potential. So it's quite a lot of things here to do. What I'm presenting is when everything is bounded. Yeah? And it would be nice to develop it for more complicated story. And in fact, even for nonlinear Schrödinger equation was a long, long way from bounded potentials to potentials like Coulomb bounded, I suppose, the 70s by Spohn, and about 10 years ago appears a result for Coulomb, say, potential. Well, anyway, for this equation, this is third main theorem. We have well-posedness for this equation. Yeah, we have unique, strong solution with initial data. And yes, application infinite dimensional operator value. That's what I'm also inviting you to look at this equation. Yeah. So this part you see here, A depend on eta, and eta is the expectation of solution. So if you know you're well familiar with Makin loss of nonlinear diffusions, then you directly realize that this is exactly the kind of term which appears in Makin loss of nonlinear diffusion. So this is nonlinear Makin loss of diffusion, but you see in this operator valued infinite dimensional complex value story. So here, therefore, is an example of infinite dimensional Makin loss, how one can deal with them. Well, okay, so as I say, I presented you as a conclusion, I presented you here the main result of well-posedness of various kinds of stochastic nonlinear infinite dimensional equations. And the use of this is in the theory of quantum control of interacting particles and quantum mean field games. Thank you for your attention.
Thank you very much. I have to stop the recording.